Okay, so welcome to the induction lecture. We just finished taking up the midterm. So we're going to move on to induction. You might recall last week, we finished off with magnetostatics, where we talked about all the properties of a static or a stagnant magnetic field, where you have to have a moving charge or a current to feel any sort of magnetic force. And we've done that chapter now. So now we're going to move into analyzing what happens when you have a changing magnetic field and some properties you might get with that. Okay, very quick announcements before we do that. There's one, this tablet is very slow at the moment. I just want to make a very quick announcement. I don't know why. Let's try this again, shall we? Okay. Logging you in. It was logged in before. I don't know, maybe the cookie ran out or something. I don't know. Okay. Where's our course? There's our course. Okay, so very quick announcement. I haven't updated the schedule, like the PDF of the schedule yet, although I just remember now I probably should. I just want to point out that assignment 3, let's see here. I changed the due date for assignment 3 to Saturday, August 1st at 7 p.m. I pushed it back 24 hours. And this was in light of Eid is apparently either on Thursday or Friday, depending exactly on how things sort of shake out and, with the moon, which is actually physics. So, maybe if we wanted to study some celestial physics, we can figure out exactly what day it'll fall on, but that's besides the point. With the midterm last semester with 136, we weren't able to move it because the Saturday or the Sunday, the two possible days we had for the midterm, both of which were the possible days for Eid. So you were always making, like, you couldn't just avoid Eid altogether. Saturday or Sunday was still 6 of one, half a dozen of the other. But with the assignment, it's not an individual assessment. Time zones aren't a thing. So we could easily push it back by a day. And like student conflicts also aren't a problem. We couldn't hold the midterm on the Friday in 136 because there were a lot of other classes that students were taking that were held on Friday. So, we were very limited in 136 with either using that one Saturday or the one Sunday. Here we have some flexibility, right? Submitting an assignment, there's no course conflicts with anything else. It's not an individual thing. You can submit it at your leisure. So we can easily push it back by a day. So the due date is now Saturday, August 1st at 7 p.m. It's just pushed back 24 hours. So hopefully for those of you who want to celebrate Eid on the Friday, you can do so with confidence. You're not missing out on any time. You have an extra 24 hours to replace that time you would have spent with your family during Eid. So that's the only announcement I really wanted to announce. Okay, induction. Let's start with induction. Will it scroll? No, it won't scroll. Let me try minimizing. Okay, there we go. Okay, so I want you to recall a little bit. Look at the course picture that we have on the Canvas page. This is the course picture that we have on the Canvas page. And I told you way back at the beginning of the semester, I think it was like either the first or second lecture, that I think it was when we learned about a Faraday cage. I drew your attention to this course picture. And I don't just pick pictures willy-nilly. Like there's a very clear reason why I picked these pictures. And I told you we would be learning about a Tesla coil and how they worked in this class. And we are right on the cusp of finishing finishing all the material we need to explain how this works. So what's going on in this picture? Just a rundown. There's a Tesla coil, and the Tesla coil's main purpose is to generate sparks or lightning. And the lightning is arcing across an air gap to a metal cage that has a person inside of the metal cage that is unharmed with the metal from the lightning striking the metal cage. So the lightning arching across an air gap we've talked about. we said that yes, air is an insulator, but with enough voltage, you can push current through anything, whether it be wood or air, which is what we see all the time with lightning and thunderstorms. So we talked about that. Why is it striking the metal cage? Well, the metal cage is a conductor, and that has the minimum resistance to ground. So electricity will always travel the path of least resistance. So it'll travel through air because it needs to, but it'll strike the cage because it's the closest conductor. So it'll strike the cage before anything else. There's a small caveat to that this wire here, oh, you can't see that. This wire here is also a conductor. So you have to make sure the cage is, like the air gap between the Tesla coil and the cage is shorter than the air gap between the Tesla coil and the wire. And if the air gap is shorter between the Tesla coil and the wire, it'll just jump to the wire because path of least resistance. It will not want to travel through a longer stretch of air gap when it doesn't have to. So we talked about that. The person inside is unharmed. We talked about that. We talked about a Faraday cage and why that's true and stuff like that. The only thing we haven't talked about is how a Tesla coil works. So most of the course picture, you should be fully able to describe the physics of what's going on in the picture here. The only exception is at the moment, you don't yet know how a Tesla coil works. So that's what induction is going to help solve. Okay, so let's consider the following. Normally I would do a demo in person for this. We have all this equipment at school and I would bring it in and I would show you in front of your very eyes in real life. However, we have to settle for a video. So let's see if I can get this working. And I have to change the screen sharing. There we go. Okay. Okay, so you see here, there is a solenoid or a coil, which we've analyzed with Ampere's law in the previous lecture. And it's hooked up to a very simple circuit. The circuit is just an ammeter, which measures current, and the coil itself. There's no battery. There's no battery in the circuit. And you see in the video, someone is pushing in a bar magnet into the center of the coil and then pulling out the bar magnet. And you see on the ammeter, it's currently measuring microamps. So it's a small current. Micro is times 10 to the minus 6. It's a small current, but it's a current nonetheless. And he is inserting, what I assume is a he, that looks like a male hand, is inserting a bar magnet. And when he inserts the bar magnet, you see the needle on the ammeter moving. And then when the magnet is stationary inside the coil, there is no current. But when he then removes the bar magnet, you see a current again. So I'm just going to play it for a few more seconds so you can kind of see that. Okay, so pretty simple video. Usually I would do this exact demo in person, but really what I was wanting to show you here is that if you have a simple circuit where you just have a coil with an ammeter measures current and nothing more, no battery, you can still somehow get a current, even though you don't have a battery or an electromotive force or something to move the charges. So the question there is, what's going on? How do you get a current when there's no battery? You can do a few more experiments and you can figure out what kind of factors influence the amount of current that you get. And we'll talk about that a little bit later on. However, let's just do a sort of loop back to Maxwell's equations. I told you at the beginning of this course that the field of electromagnetism is governed by 4 equations. The first of which was Gauss's law, which we looked at. That's for electrostatics. And this allows you to relate the electric field that you obtain or that is generated by the source of the electric field being charged. So this was the first one that we looked at. The second one we looked at was Gauss's law for magnetism, and this mostly governs magnetostatics, where if you just have a magnetic field that is not changing with time, this tells you that they have to be closed field lines. So they don't have to be circular, but they've got to be closed. They've got to loop back around. And this also tells you that there's no source of magnetic field, in the same sense that there's a source or a starting point for the electric field. You know, if you draw a proton, that's the source, that's the starting point of an E field, and they go on either for infinity, or the end point would be a negative charge. They don't loop back around home. So this is telling you you also cannot have magnetic monopoles. Then we skipped and we went down to Ampere's law. Ampere's law is kind of interesting. Ampere's law told us that a moving charge, or a changing electric field, presumably, a moving charge or a changing electric field governs or predicts that you're going to induce a B field. So this says a changing E field produces a constant B field. Oh, well, whatever, constant B field. So a moving charge, a stationary charge, will be emitting an E field. And if you move that charge, the magnitude of the E field is constant, but it's changing because the vector nature is changing. Another way to do it is to literally vary the intensity of the strength of the E field as well. The same ideal is going to induce a B field as well. So the only one left we have to talk about is Faraday's law, the Faraday's law of induction. So Faraday's law of induction says if you take the electric field E and you integrate it along a line like f of x dx, the integral of f of x dx, you've presumably, as a summer physics student, you've presumably had exposure to first-year calculus. Even if you're concurrently taking it now, by now you would have at least hit some sort of integration. So everyone should be familiar with the notion of an integral of f of x dx. So that's all we're doing here, is we're integrating the E field over a horizontal distance. And this is going to equal the rate of change of magnetic flux. Well, we know what magnetic flux is. We saw it earlier, right, with Gauss's law for magnetism. The magnetic flux is how many magnetic field lines are traveling through a surface or passing through a surface. So, you know, if you had a surface and you had, you know, a magnetic field passing through on an angle, how many field lines are actually passing through here? It's going to be BA times cos of the angle between the normal of the surface and the magnetic field. So we have this quantity, magnetic flux, psi sub B, magnetic flux. And if you take its rate of change, its derivative with respect to time, then that tells you you're going to get an E field. So Faraday's law of induction says a changing magnetic flux produces a constant E field. And that's really interesting because Ampere's law says if you have a changing electric field, you get a constant B field. Constant B field. So that constant B field is not a changing magnetic flux, it's a constant magnetic flux. So that alone doesn't necessarily cause a vicious cycle. But we will talk about the vicious cycle in the next chapter. Faraday's law says the exact opposite. Still really cool. Faraday's law says if you have a changing magnetic flux, you get a constant E field. And that I just think is just super, super cool. That it kind of works both ways, was what I'm saying. So this slide, sorry for all the jolty, there we go. So this slide pretty much sums up what I just said here, that a changing magnetic flux induces an E field. Now, let's just say this E field happens to be inside of a wire, okay? A wire, if there's an E field in a wire is a conductor. A conductor means it does not resist the flow, meaning if there's a little bit of a push, boom, those charges are gonna move. So if there's an E field in a wire, what does the E field cause in a wire? It causes motion. Motion of charge. And motion of charge is the same thing as a current. So there you go. Now, so pretty much what Faraday's law is saying is if you have a changing magnetic flux, you can actually induce motion of charged particles in a wire, which means you can induce a current in a wire, which is exactly the demo that you were seeing just a few minutes ago, is that when the magnet was being inserted into the solenoid, you were changing the number of field lines that were passing through the solenoid. When the magnet's really far away, very few field lines are passing through the solenoid. When the magnet is really close, even if it's inside the solenoid, then all of the magnetic field lines are passing through the solenoid. And thus has a changing magnetic flux. You went from having few field lines to a lot of field lines, so that's a changing flux. And that induced a current, as you saw in the ammeter. So the first slide up here asks you a question. It says, what factors influence the observed current? So now that we know what equation governs this behavior, it's Faraday's law, let's see if we can sort of figure out what factors exist that can change the current. Well, we know the source of the current is a changing flux. Flux, as I said, is BA cos theta. There are three variables in that equation. So there are three factors we can take advantage of to change the flux and to affect the current. The first one is to simply just change the B field. You know, you don't have to move a magnet in and out. If you had some ability to just crank a dial or crank a knob on a piece of equipment and just make the B field stronger, that'll do it. If you increase the strength of the magnetic field, you will change how much flux goes through a certain region of space. Another way to change the amount of flux passing through a surface is to physically change the area of the surface itself. So if you had like a loop of wire, we know circles are the most optimal geometric shape. You know, if you take that circle and you sort of stretch it, it just becomes a very narrow line with a little thin gap. So, you know, if you take a circle and you stretch it, you're going to get something that looks like this. Same perimeter, 2 pi r, 2 pi r. It's the same amount of wire, but this area is much, much bigger than this area. You know, so you can change how much area a loop sort of creates by changing the shape of the loop. So you can physically just change the area. And the more drastic of an area that you change, the more of a current you're going to get. People might be thinking, oh, well, circles are the most optimal shape. So if I deform the circle, I want to make sure I don't deform it too much. That's not true. You actually want to deform it a lot because it's the change in flux. The bigger the change, the bigger the derivative. And the bigger the derivative, the bigger the E field, according to Faraday's law. So you want to maximize the change in flux to maximize the current. And then the last variable here is change the angle. So, you know, let's say we talked about DC motors last lecture on Thursday. So if you had a loop of wire that was sort of on an axis that could spin, then you could literally have a loop that spins. And if you had a constant magnetic field and a loop of wire that spins inside of it, then what you're doing is you are changing theta. And if you change theta, you're constantly changing how many magnetic field lines are passing through the loop, right? Because as the angle goes from 0 to 90, the flux will go from a maximum to 0, which is a minimum. So that is 3 different ways that you can change the flux, and thus 3 different factors that contribute to how much current you're going to get. Now, another way to represent Faraday's law is, well, the left-hand side of Faraday's law was the integral of E dot dl. That quantity, if you consider what we've talked about before, this quantity E, well, we know what E is just E, and dl is a length, okay? So let's call it like d, distance d. Well, is there a formula we sort of looked at or have previously that is E times d? The answer is yes. If you recall, in a parallel plate capacitor, we have the electric field in a parallel plate capacitor is delta V over D. Or more specifically, ED is E times displacement, E times distance, is going to be delta V, voltage. So Faraday's law has this sort of E times D. Now, there's more calculus involved. There's, the dl, the integral of dl will be L. L is a distance, length. But there's a dot product, so there's a cos involved. So yeah, there's a little bit more than just E times D. But I'm showing you that the left side of Faraday's law is very, very, very similar to this equation here, delta V equals E times D. So I'm using this equation to help explain to you that the left-hand side of Faraday's law is voltage, V, volts. It's exactly the same units as volts. In fact, it is volts. You can think of it as exactly what a battery does. Now, you may have heard the term EMF, electromotive force. And in physics, we use the symbol. I don't even know what the symbol is called. It's not, I don't think it's a Greek letter. I think it's just like a math symbol, weirdly enough. But the sort of cursive capital E, we call that EMF. It's voltage. If you are more comfortable with using the symbol delta V, just like we did before, go nuts. That's totally fine. The logic behind using this cursive E instead of volts, V, is we want to distinguish to the reader the difference between a voltage from, let's say, a battery versus the voltage due to induction, Faraday's law of induction. So everywhere you see sort of like a cursive E, typically in physics, that usually refers to the fact that it's an induced voltage. But even in physics, we don't even use that consistently. Some physicists will use script E for all voltage, whether it be from a battery or whether it be from induction. So even physicists honestly can't even agree on symbology in that one. So I will try hard to use script E, cursive E, when I'm talking about an induced voltage, and I will try hard to use delta V when I'm talking about a constant voltage, like a battery. If you feel more comfortable using whatever symbol you want to use, if you want to use script E for everything, go nuts. If you want to use delta V for everything, go nuts. That's totally cool too. Okay, back to my point. Now that we know the left-hand side of Faraday's law is induced voltage, then I want you to sort of think of a small little caveat. Here, we're talking about the changing magnetic flux causing a voltage. If you have a coil, and a coil has many, many loops, let's say n equals 10 loops, then each of those individual loops will be feeling the same changing flux. If you had a bar magnet here, like a north pole of a bar magnet, and this bar magnet was coming closer, then each loop, oops, loops do not start with a P. Each loop will be feeling the same amount of derivative d phi by dt. Each loop will feel the same changing flux. So you could say the total induced voltage is going to be N times the induced voltage in one loop, which is simply just N times d phi by dt. Now, the last thing I want to draw your attention to is the negative sign. And we'll come back to the negative sign later in the lecture. I don't want to just pretend like I'm ignoring it and not explaining it. So I will draw attention to it now and say we will come back to it at the end, later in the lecture. Okay, I've been doing a lot of talking. It's 10, it's just after 10 o'clock now. So I want to see kind of where you guys are at. So I'm going to launch a poll. Although before I launch a poll, let me just shrink the slide here. So when I launch the poll, you can still see it. Okay, so I'm going to launch the poll. Okay, so you should see something up on your screens now. So here's a question. In order to change the magnetic flux through the loop, what would you do? So given the diagram there in the slide, would you drop the magnet, move the magnet upwards, move the magnet sideways, only A and B, or all of the above options? Oh yeah, the Jeopardy music. I keep remembering in the moment about the Jeopardy music. Okay, about 22 of you have voted. 23 of you have voted. Okay, so it's been of 25, 26, 27. Okay, so these aren't marked, right? I don't even know who's participating. So for the interest of time, I'm going to end the poll momentarily. And I'm going to share the results. Okay, so there you go. You should see the results on your screen. So it looks like a set of steps. It gets bigger and bigger as we go down. 7% for A, 7% for B, 7% for C, 30% for D, and then 48% for E. So that's kind of interesting. Now, if we look here, we need to change the flux. So how can we change the flux in this situation? Well, if you drop the magnet, oh, you can't see blue very well. If you drop the magnet, look how many field lines are going through this loop right now. The magnet is so close to that little loop of wire that all of the magnetic field lines coming out of that magnet are going through the loop. So if you were to drop the magnet, and let's say the magnet is sort of down over here, then some of the field lines will miss the loop. Now, of course, some of them will still go through the loop, but many of them will not anymore. So that would be a decrease in the number of magnetic field lines through the loop. That would be a decrease in magnetic flux. So yes, this one would induce some sort of current. Now, if we move the magnet upwards, same thing. If we move the magnet upwards, we are, let's say there's a 1 or 2 centimeters of gap between the magnet and the loop. Well, if you moved it a little bit closer, you're getting it that much stronger. So again, it will increase the flux. Or alternatively, if let's say your perception, you're like, hey Mark, I didn't know there was a space there. It doesn't matter. Let's assume the magnet is in the middle of the loop and there isn't a space. Well, if you move the magnet upwards, then it's leaving the coil, right? Or it's leaving that one loop. And thus what is a maximum flux would then become less maximum. It would become smaller, and that would be, again, a change in flux. So in either case, this one would also work. So the answer could be D, I suppose. However, if we look at C, if we move the magnet sideways, well, if we move the magnet, same altitude, if we just move the magnet to the right or the left, doesn't matter, then the field lines coming out of there would, part of them would still be going through the loop, as you can see here on the left-hand side of my drawing. Part of the magnetic field line would still be going through the loop as before, but many of the field lines now are missing the loop altogether. So that would also change the total number of field lines going through the loop. So all of those will result in a change in flux, and thus all of those will result in a current. Okay. Oops. There we go. Okay. I think hopefully you can still see my screen. Okay, now, one thing we haven't talked about, and I sort of implied this notion, if you were inducing a voltage in a conductor, then a conductor will allow electrons to flow and you're going to get a current. So here you can use Ohm's law to predict current. So you can say Ohm's law is V equals IR. Now the voltage is not due to a battery. So, you know, again, using my notation of wanting to emphasize when there's a battery versus when there's induction, Ohm's law can then be written as the electromotive force equals IR. Okay, so given this sort of notion, I want to do another poll. Oops, come on. I want to do another poll with you guys to see how you answer this question. So I'm going to launch a second poll. Oh, nope, not share results. Sorry, relaunch the poll. Okay, so there's the poll, should be live on your screen now. The second question is, wire 1 has a length of L and it forms one loop. And a bar magnet is then dropped straight through, in and then out. Wire 2 is twice as long, but it forms two loops. And the same magnet is dropped through the loop, right through, in and then out. Compare the magnitude of the induced current in these two cases. And again, with the Jeopardy theme song, I always remember when it's too late. Okay, so remember Ohm's law, V equals IR, or EMF equals IR. And we talked about what EMF is, right, with Faraday's law. 24 of you have responded so far. We had slightly more last time, but only slightly. 25 of you. Okay, now 27. Okay, I think we're at the same number we had last time. So I think that's good enough to call quits. So I'm going to end the poll. If you didn't get a chance to respond, that's okay. I don't know where the other few of you are. Maybe you were thinking, maybe you were getting a drink or something. I don't know. So let's share the results. So a majority, 67%, a majority of you voted C, but a total of about 34% of you voted other than C. Now, interestingly, no one voted D, which I thought was good. It's good because D is not right for sure. So let's stop sharing the results. So spoiler alert, the answer is C, but let's see why. So Faraday's law says the induced voltage, EMF, is going to equal the number of turns times the change in magnetic flux. Now, each loop in case 1 and case 2, each loop has the same B field coming in because it's the same magnet. Each loop is the same area, and each loop is oriented in the same direction. So each loop has the same set of three variables, B, A, and theta. So this quantity here is the same in case 1 and case 2. However, what's different is in case 2, we have two loops. Two loops means n equals 2, which means in case 2, we're actually going to get twice as much voltage that is induced. Now, here's the kicker. Yes, there's twice as much voltage that's induced, which you might think the answer is B. Twice as much voltage, twice as much current. Because you're thinking to yourself, Mark, V equals IR. If you have twice as much V, you're going to have twice as much I. Well, you're right if everything else remained constant. However, recall R. right? Remember in the first chapter, electrostatics, or I guess it was circuits, so maybe well, somewhere in there, somewhere in circuits, we looked at the resistance of a piece of wire is going to be rho L over A. Rho of the wire, the cross-sectional area of the wire, and then L, the length of the wire. So in case 1 and case 2, it's the same copper wire, presumably, so rho is the same. It's the same gauge of wire, so the cross-sectional area is the same, but it's a different length of wire. We're told in the problem that the length 2 is twice as long as length 1. So this means resistance 2 is twice the resistance of 1. So if you use Ohm's law, you're going to get 2 times the induced voltage, and that's going to equal I2, but the resistance is 2 times the first resistance. So when you plug everything in, you end up getting electromotive force 1 equals current 2 R1. But Ohm's law says in the first scenario, E1 equals I1 R1, which means I2 equals I1. So the answer there is going to be C. They're both equal to each other and non-zero. Okay, now I drew your attention to the negative sign in Faraday's law. I'm just going to redraw Faraday's law so your brain has the ability to sort of see it written down multiple times. Okay, so there's Faraday's law. Lenz's law, quite simply, is the negative sign of Faraday's law. That's all it is. And I explained, you know, Faraday's law is one thing. We understand that a changing magnetic flux will induce an E field. But why? Why is there a negative sign there? That is Lenz's law. Lenz's law says an induced current, as a result of Faraday's law, an induced current will have a direction such that the magnetic field that this induced current produces will oppose the change in magnetic flux. Now that's a lot of words to think about. One other thing I want to say about Lenz's law before we do a conceptual example is Lenz's law is what I would call, oh, you can't see the green. Lenz's law is what I would call the qualitative version of Faraday's law. Faraday's law is the quantitative, quantity meaning a number, I can come up with a value. Faraday's law is the quantitative version of Faraday's law, meaning it comes up with a value, how much voltage is induced. Lenz's law is the qualitative, meaning I don't care about the number, I care about the attributes. And Lenz's law is what predicts the direction of the induced voltage and thus the direction of the induced current. So I said here that Lenz's law says that the induced current opposes the change in flux. What does that mean? So here's a conceptual example. Oops, what happened there? Okay, what does that mean? Let's take this for instance. If you had a bar magnet that was positioned underneath a loop, and what you do is you move the magnet upwards. Well, we've already done a polling question with this. We understand that when you move the magnet upwards, you are increasing the number of magnetic field lines that are passing through the loop. So in this case, the change in flux, or let me say case A in panel A, the derivative in the flux is going to be positive. Oh, not bigger than 1, bigger than 0. okay? So the change of flux is going to be positive. The number of field lines that go through the area are increasing. It used to be something like 5, now it's like 10. So that change is positive. The derivative is positive. Faraday's law has that negative sign, which is Lenz's law. Lenz's law says that the current that you induce will oppose the change in flux. So what does that mean in this case? Well, in this case, we have more north. We have more north upwards. We have an increasing amount of north magnetic field lines. We want to induce a current to reverse that. We want to induce a current such that the induced magnetic field from the current will have north pointing down to combat, to oppose this change. So in this case, we know the magnetic field lines are increasing upwards. So our desire here is to have induced B field. Oh, you can't see it, it's getting all scratchy. Induced B field downwards. That's what we want. Okay, so then we think to ourselves, we know Ampere's law, we know our right-hand rules. Which direction of current in this loop, let me redraw this over here. Here's a conducting loop. We have our desired B field from the current pointing down. Which way does the current have to flow so that that current's B field points down? Use your right hand. There's a few right hand rules you can use. I'm going to use the one where you give yourself a thumbs up. Where you grab the wire with your fingers and your thumb points in the direction of the current. If you grab the wire, your fingernails have to point down inside of the center of the loop. So if you have your right hand, here's your arm here, I don't know. And your fingernails point down, and your thumb is going to point in this direction here. So this says if you move the bar magnet upwards and you're increasing the number of field lines, then Lenz's law says you want to decrease the number of field lines. You're going to want to induce a B field downwards. And in order to do that, the current is going to be traveling clockwise. So that's what we see here. The current is coming down and traveling clockwise, coming up back this way. Okay, so that's what it means to oppose the change. Now, similarly, if we have the bar magnet in the same starting position, but we move it down farther away, then we used to have, let's say, something like 5 field lines going through the loop. Now we only have something like 1 or 2 field lines. We've lost field lines. And Lenz's law says you want to induce a current to oppose the change. So if we're losing field lines, you want to induce a current in such a way that it increases the number of field lines. So in panel B, we want to induce a B field, B ind. We want to induce a magnetic field upwards to oppose the change, to oppose the loss. Well, which direction of current makes this true? It's the opposite direction, counterclockwise. Again, by your right-hand rule. And if there's no movement, again, Faraday's law says it's the change in flux. Lenz's law says you want the direction of current that you induce is in such a way that you oppose the change. If there's no change, there's nothing to oppose, and the current doesn't have to do anything, so it doesn't exist. This is very similar to Le Chatelier's principle in chemical equilibria that you learn in first year chemistry. So, you know, in chemical equilibria, you know that if there is an equilibrium going on, if you remove products, then the equilibrium will shift or move in such a way to oppose the change. So if you change the products by taking some products away, then the chemical reaction will speed up and try to make more products. And that's exactly what's happening here. If you remove some of the field lines, then the current will move in such a way that it makes more field lines. So you can think of it exactly like Le Chatelier's principle, but in physics. Or if you're a physicist and you don't necessarily like comparing things to chemistry, you can think of it like a baby or a young child that doesn't like change. You know, like, hey, we're moving houses, and the child is like, no, mommy, this is my house. I don't like change. So they'll resist change. In fact, it's kind of human nature to resist change at any age. So I view Lenz's law a lot like human nature. You know, we like our comfort, we like our dependability, we like our world to be, you know, dependably consistent. And when it changes, that's when there's a lot of uncertainty and stress and anxiety in our lives. So I view Lenz's law like human nature, but if you want to view Lenz's law like Le Chatelier's principle, that's also equally valid. Okay, now another example, which is pretty much the same thing that we just described. I just want to reiterate it with a better diagram in case my drawing was absolutely crappy and you weren't able to follow. So here's exactly the same explanation, just with a better diagram. Let's say there is a B field that is pointing upwards. Okay, so that is what all of these are. There is a B field that is pre-existing upwards. Okay, now let's say someone cranks the strength of the B field, and they now make it stronger. So you see here that there is a change in the B field, and they're cranking the B field to be larger in the same direction as before. So that's an increase, right? That we are increasing the amount of B field upwards. Well, Lenz's law says we want to induce a B field in such a way that it opposes the change. So if the change is upwards, then the B field we induce wants to be downwards to oppose that change. In a lot of ways, it's very similar to also the conservation of angular momentum, where if you have an induced angular momentum vector up, if you change your angular momentum vector so it's larger upwards, then you're going to get a counter torque in such a way that you can get an induced angular momentum downwards. It's very similar to that notion as well. So our induced B field needs to be downwards. So if it needs to be downwards, then what direction of current is in the loop to make that happen? Again, you use your right-hand rule, grab the wire, fingernails in the direction of the desired B field. In this case, your fingernails are going to point downwards. And if you grab the loop with your right hand, your thumb is going to point in that direction. Okay, you might be asking yourself, why? Why does nature know? Why does nature work in such a way that it has to oppose? Who says? And a good chemistry student would actually ask a chemistry prof the same question about Le Chatelier's rule. You know, why? You know, the chemical equilibrium is not sentient. They don't want anything. We use the phrase want because it's easier to convey. Same thing in physics. Nothing is alive, nothing is sentient, nothing has a brain. You know, want is a bit of a loose term here. So what is it about nature, something that is not living and something that can't do anything with logic? What is it about nature that forces this to be opposite to the change? So here's a quasi-proof. And, you know, students in this class are not hardcore physicists. So complicated math aside for a second, here's a very hopefully satisfactory explanation of why this is true without sort of confusing you with complicated math. So what I'm going to do here is something called a proof by contradiction. And this is more of a philosophy technique, and it's called philosophy instead of science because it doesn't explain why something's true, it just explains that something is true. Okay, so it's not science in that it doesn't explain fundamentally why it's true, but a proof by contradiction usually is good enough to at least prove to somebody that something is true. So that's what I'm going to be doing here. Proof by contradiction. Let's assume for a second Lenz's law is false. Let's assume for a second that the induced B field, or the induced current, which will in turn induce a B field, is in a direction such that it does not oppose the changing B field. Okay, so let's assume it's false, and let's see what happens. Well, if you take a conducting ring, here, the total flux is equal to 0. And let's say we drop it. We let gravity do the work, and we drop it. Well, if we drop it, it's falling. And at some point in time, like let's say here halfway in, the magnetic flux is now non-zero. Well, I shouldn't say positive or negative. I should just say non-zero. Okay? So that's a change in flux. Okay? That's a change in flux. Now, we are, well, okay, I'll come back to that explanation in a second. I'll go through all the panels and kind of explain what's happening. Then, when it's going to continue to fall because gravity keeps pulling it down, so then when the conducting ring is fully submerged in the B field, then this flux equals a maximum. You could not possibly be pumping any more field lines through this area as you already are. Okay, and here, when it falls out here, you went from having many field lines to slightly fewer field lines. So this is going to have the same amount of flux as we had in panel 2. So these two here are going to be equal to each other. And then, of course, after it falls through, then we are going to come back to having 0 magnetic flux, 0 field lines through the ring. So the question is, in which direction is the induced current in these scenarios? Well, proof by contradiction. Let's assume it's not opposite. What happens? Okay, we really only need to look at one of these like a pair of these panels to figure it out. Let's look at the first 2 panels for a second. What is the changing flux? Negative or positive aside, just what's the changing flux? Well, we went from having no field lines to many field lines, right? Here we have nothing. Oh, you can't see that. Here we have nothing, and here we have something. Okay, so this change in magnetic flux is positive. Okay, now let's assume for a second that the induced current reinforces this change. Okay, well, we've increased the number of field lines into the page, right? We used to have no field lines into the page. Now we have 6 field lines into the page. 1, 2, 3, 4, 5, 6. So we have increased the number of field lines into the page. Let's assume we induce a current to reinforce that. I want to induce a current that adds field lines into the page. Okay, the induced B field then, we are assuming is into the page. So you take your fingers and you point them into the page, because that's what we're wanting. We're wanting the induced B field to be into the page. And then we wrap our thumb around, and our thumb points in the direction of clockwise. Okay, so if we prove by contradiction, if we assume Lenz's law is false, then we predict that the induced current will be clockwise, and that the magnetic field as a result of this current will again be further into the page. But that causes a feedback loop, because only 6 field lines were into the page, which was already a change from 0. If you induce a current where the current itself is contributing to B fields into the page, then that 6 might become 8 or 10 or something like that, which means you have even like a propagated or a chain reaction increase in magnetic flux. So that's what's happening here. I'd say, well, if Lenz's law is false, then the induced B field will be into the page in panel 2. And this will result in a clockwise current. Here's the problem, though. Or here's the contradiction, proof by contradiction. Here's the contradiction. However, this newly induced B field will continue to add B field lines into the page. And this will then in turn cause a further changing flux. So if you have a further changing flux, then Faraday's law kicks in a second time, and then you have a even more induced current to keep up with the changing flux. And we've already said the current is going to be clockwise. And then when you induce even more current clockwise, it's going to induce even more of a B field into the page, which is going to have an even more changing flux, which is going to induce more of a current, which is going to induce more of a flux, which is going to induce more of a current. Eventually, what you end up getting is you get something called a positive feedback loop, and you're going to get current tending toward infinity. That's impossible. There's no such thing as an infinite current. And this here is exactly the contradiction. We know that this isn't true. We know that there isn't an infinite current. Because if there's an infinite current, that would be amazing because we could have a lot of free energy. We could just drop a small conducting loop through a small magnetic field and then all of a sudden power the entire world. We empirically know that this does not happen, which we know empirically that Lenz's law must be true. It must reverse. So that's why I said a quasi-proof. A quasi-proof means I can show you that it's true, but it doesn't explain why. A more fundamental reason for why, now that you know the problem is you get an infinite current. The reason fundamentally and physically and in nature, the reason why Lenz's law is to oppose the change is because it's a conservation of energy argument. If you had an infinite current, that would take an infinite amount of energy. Not only is there no such thing as an infinite amount of energy, the other notion of conservation of energy is the total amount of energy in a system is conserved. Ultimately, where is the energy coming from that generates this counter current? Ultimately, it's coming from gravity, right? If you look at conservation of energy, the loop has dropped a distance, delta H. So it's losing mgh worth of joules of potential energy. And that energy is being transformed using Faraday's law. That energy is being transformed into electrical energy, meaning a current. There has to be a sort of equality there because conservation of energy, where the system loses energy in one aspect, it gains energy in another aspect, right? Conservation of energy. So fundamentally, how does nature know? Conservation of energy. But I had to explain this proof by contradiction to you to explain why conservation of energy is the correct interpretation. The issue here is, if the current was to reinforce the change, that would cause a positive feedback loop and eventually you would get an infinite current. That requires energy, And that's what led us to the conclusion that fundamentally, how does nature know Lenz's law is reversed? It conserves energy. So hopefully that sort of explanation makes sense. Okay, there is another right-hand rule that we're about to learn for the induced current. So here, I'm talking with Lenz's law, I'm saying, look at what the changing magnetic flux is, and then oppose it. And we talked about be induced, right? So here, you can point your thumb in the direction of the induced magnetic field. So in the previous example, up here, the induced magnetic field is downward. So point your thumb downward with your right hand. And then if you wrap your fingernails in the natural direction that they bend, then your fingers and your fingernails are going to point in the direction of the induced current that you get as a result of Faraday's law. So that's what this is saying here. So this diagram and this slide is saying if you happen to have an induced current that is upwards, you point your thumb upwards, wrap your fingers around, and you see that the current is going to follow the same curl as your fingers. Okay, so let's move on to a concrete example. Let me just shrink this a little bit. Okay, here we go. So a square loop of wire that has a side length of 5 centimeters is in a uniform magnetic field known to be 0.16 Tesla. What is the magnetic flux in the loop? Okay, so words and physicists don't mix very well. So we have L, uniform magnetic field of whatever field strength. Okay, so B field equals 0.16 Tesla. Okay, A, what is the magnetic flux in the loop if the B field is perpendicular to the face of the loop? Okay, so A, magnetic flux equals BA cos theta. If the B field is perpendicular to the face of the loop, then it's as I've drawn in the diagram. The B field is into the page, the loop is laying flat on the page, so the angle between that is 0 because the angle is the normal to the face. So the normal to the face is into the board or out of the board, so it's either 0 or 180, it doesn't really matter. So the flux in this case is going to be B times A, which is going to be 0.16 times A, what was it, 5 centimeters? So 0.05 squared, which is going to be 0.16 times 0.025. And if you multiply those, I think you're going to end up getting something like 4 times 10 to the minus 4 Weber. Weber is the unit for flux, magnetic flux. So that one's pretty simple. B, what is the magnetic flux through the loop if the B field is at an angle of 30 degrees? Okay, well, if the B field is at an angle of 30 degrees, then that's something like this. Come on, there we go. Something like this. So there's 30 degrees between the B field and the surface of the loop. So here, B, we're doing the same calculation. Flux psi sub B is going to be BA cos theta. It's going to be the same B field, the same A. However, it's going to be times cos of 30. And cos of 30 is going to be √3 over 2. So this is going to be 4 times 10 to the minus 4 times √3 over 2. So this is going to be what, 2 over √3 times 10 to the minus 4. And √3 is 1.7-ish. So, you know, 2 divided by 1.7 is going to be just over 1, like 1.7 1.3 or 1.4. I'm getting 3. Oh yeah, something slightly less than we had before. Yeah, so we had 4 before, so something slightly less than that would make sense. So it's 3.5 times 10 to the minus 4. Oh yeah, because 2 over 1.7 is greater than 1. Yeah, that makes sense. Okay, and then here, what is the magnitude of the average current in the loop if the loop is known to have a resistance of who cares what that number is? And it is rotated from position B to position A in some amount of time, whether it be 10 seconds or 0.14 seconds or whatever. So part C is, what is the current in the loop? Okay, well, we know Ohm's law. V equals IR. V is not by a battery in this case. V is actually through the electromotive force, the induced voltage. We want to know the current, so I equals EMF over resistance. We're told in the question that the resistance is 0.12, so that's good to go. And then here we have, what is the induced EMF? Well, Faraday's law says N times the derivative of flux with respect to time divided by R. How many loops do we have? I think it's just the one. Yep, A square loop, so 1 times, and the change in flux with respect to time. Well, this is going to be the change in flux over the change in time divided by R, and the change in flux is going to be BA times cos theta minus 1, right? Because it's the answer from part B minus the answer from part A. The answer from part B is BA cos theta, and the answer from A is BA. So it's BA cos theta minus BA, which is BA times cos theta minus 1. We know the numerical answers for this as well, so we can plug that in momentarily. Over delta t, what was delta t? Delta t was 0.14 seconds. Well, who cares? I'm just going to write delta t for a second. Over r. And the answer to part B was 3.5 times 10 to the minus 4. The answer from part A was 4 times 10 to the minus 4 over delta t. Delta t was 0.14 all over r. What was r? 0.012, I believe, something like that. And if you plug all that in, you're going to end up getting 3.6 times 10 to the minus 4 volts. Okay, if you wanted to keep it as a formula, which I strongly recommend doing, your final formula would be something along the lines of BA cos theta minus 1 over R delta T equals current. Oh wait, what are they asking for? Find the magnitude of the average current. Oh, sorry, I'm solving for current. So I was reading the wrong answer here. It'd be 30 milliamps. 30 milliamps. Sorry, I was reading the wrong answer there. Okay, so there's your final derived equation. Okay, so quick recap of what we've done so far. We've learned today that a changing magnetic field will induce a constant current, and that's really crucial. There's two pieces of information there. A changing magnetic field produces a current. A constant B field does nothing. Okay, if you have a constant B field, we're thrown back into magnetostatics, and then that's when we have Gauss's law for magnetism. And Gauss's law for magnetism is really boring because the right-hand side of Gauss's law for magnetism is 0, so it's quite simple and boring. So yes, you need to have a changing magnetic field to have anything fun happen. The other thing that's interesting is mathematically, if it's a uniformly changing B field, you're going to induce a constant current. The reason what I'm saying here is induced voltage equals d phi by dt. And assuming this is Ohm's law, V equals IR, then you see here that current is going to equal d flux by dt, all divided by resistance. Okay, this is saying if the derivative is uniform, meaning the derivative is constant, meaning the changing B field is changing at a constant rate, then you're going to produce a constant current. Now, mathematically, let's look at what else this could mean. If your changing B flux is not uniform, let's say it's getting faster and faster and faster, let's say there's an acceleration to this change, then the current that it induces is not going to be constant. The current that it induces will be also changing. And that is a really interesting premise because then Faraday's law and Ampere's law sort of kick in with one another. And then there's, again, a positive feedback loop there. But we will get to that sort of implication later in the class. So I just want to draw your attention to it. Faraday's law. We covered Faraday's law today. So a changing flux will induce an EMF. There's a minus sign in Faraday's law. And the minus sign in Faraday's law is the direction of the induced B field. And specifically, it means that it opposes the original change. And it's analogous to Le Chatelier's principle. And this is more of a point of clarification for when you're doing homework. Please remember, there are two different types of B field that are happening here. There's the B field that is imposed on the loop. It's what we call the source B field or the external B field. It's just what the loop is exposed to, whether it be from a bar magnet or some user imagination for whatever's producing the B field, whatever. That's what we call the source. But then there's also the induced magnetic field from the induced current. We know from Ampere's law that a current, a steady moving charge, will produce a B field. So there's an induced B field here that we're talking about, and then there's the source magnetic field that we're talking about. Okay, we have some time left, so let's keep going. Let's do another polling question. So before I launch the poll, I am going to make this slide a little bit smaller so the poll does not intrude on your field of view. Okay, I'm gonna launch the poll now. There we go, it should pop up on your screen. Okay, if a north pole moves toward the loop from above, in which direction is the induced current? Now, please remember here, you're looking at this from above. So if you're looking at a bar magnet from above, it says the north pole moves towards the loop. That means your eyeball is staring at the south pole. The top of the bar magnet is the south pole. The bottom of the bar magnet, closer to the loop, is the north pole. It's just not visible from above. That's why the picture shows S for south, above. Okay, only 60% of you have voted. I think we had more than that last time. Okay, there hasn't been a change in people voting in a few seconds now, so I'm going to end the poll and share the results. So we have an overwhelming majority, 70% of you voted B, and B is the correct answer, that's true, but there has been about 31% of you that voted other options, either A or C. So let's look at why, because a third of the class is there's a misconception here, so that's enough to sort of take a pause. So what's happening here is the north pole of the magnet is the one closest to the loop, and the magnet is being pushed closer to the loop from above. So what's happening is you have this loop, and you have some magnetic field going into the page, right? Because the north pole is facing down, so you're going to have the magnetic field lines going in and then like looping around whatever, okay? Now what's happening is you are pushing this magnet closer. So what you're going to end up getting is you're going to end up increasing the number of field lines. B is increasing into the page. Okay, so you're increasing the number of field lines into the page. That's what you're imposing as a change. So Lenz's law and Faraday's law says the induced B field is going to want to oppose the change. So the induced B field is going to be opposing the green X's. So the induced B field is going to be out. So B induced is out of page. So we use our right hand rule. The induced B field is our thumb. Thumb is pointing out of the page. So our thumb is pointing out of the page. And we grab the wire with our right hand, and our fingernails point in the direction of counterclockwise. So there's the answer, there's the explanation. Many of you got that, so that's amazing. But I just want to make sure we were all on the same page before we moved on. Okay, here is another example. So I'm going to relaunch the poll. Oh no, before I relaunch the poll, I should shrink this so you can see it on your screen when I launch the poll. Oop, too small. There we go. So I'm going to relaunch another poll. Boom. Okay, so you should see it up on your screen now. So here's another one. A wire loop is being pulled through a uniform magnetic field. What is the direction of the induced current? Somebody voted E. There is no E. Maybe that was a slip of the finger, or maybe you were being cheeky. Either way, no problem. Okay, about 57% of you have voted. 60% of you have voted. I think last time we were closer to 80% before I ended the poll. 75%. 78%. I think this is right around the time I ended the poll last time. Okay, I don't see, 82%, there we go. Okay, so I'm gonna end the poll now and share the results. So there you go. So the majority of the answers are answer C. 65% of you voted C. However, let's see here, 35% of you voted something other than C. So that's more or less the same percentage as we had last time. So let's take a pause. Let me stop sharing the results so you can see your screen. Let's take a pause here to kind of see what's going on. So maybe for spoilers, C is the correct answer. There was no induced current. I'll tell you that right up front. So maybe for those of you who voted A, I think 22% of you voted A. For those of you who voted A, maybe you slightly misinterpreted the problem, maybe. Maybe you thought the loop of wire was going to be on its way out of the B field. And in this case, I agree with you, people who voted A. If the B field was on its way out of the magnetic field, then the change in magnetic field is you're losing magnetic field lines. So your induced magnetic field is going to want to be in a direction such that you are resisting the loss, so you're adding more. So using your right hand rule, your magnetic field would be into the page, and when you wrap your fingers around, you'd see that the current would then be clockwise. So for those of 22% of you who voted A, I'm putting words in your mouth here. Perhaps you were thinking the loop would be on its way out of the magnetic field. And if that were the case, you would be 100% correct. However, the question says the loop of wires being pulled through a uniform magnetic field. The diagram obviously has to be a finite diagram because I can't draw a diagram infinitely, whatever. But the question says it's moving in a uniform B field. So if it's traveling in a uniform B field, as it travels left and right, the change in flux is 0. The number of field lines that are going through that surface at any given point in time is not changing. So there is no induced current because the derivative of flux with respect to time would be equal to 0. I think 9% of you, voted B. I'm not sure what led you to counterclockwise, other than perhaps just a misconception about the right-hand rule and I guess the scenario and the problem. So hopefully after the explanation, that clears it up for you. So the answer is going to be C. Okay, it's 11 o'clock. I think this is a good time for a break, or like to call it quits on the lecture. So we will resume tomorrow afternoon we'll start with this numerical example to do a bit of a refresher. So yeah, thanks for coming out, and I will see you guys tomorrow.